Welcome to all of you. Now we discuss about the stability analysis of equilibrium points of a system of difference equation. The question is that consider the following first order nonlinear system of two difference equations xt plus 1 equal to f of xt yt plus 1 equal to g of xt yt, where fxy and gxy are two nonlinear functions with continuous second order derivatives in the neighborhood of x star y star, where the points x star y star be a steady state or equilibrium point or fixed point or critical point of the above system. Then prove that the equilibrium point x star y star is locally asymptotically stable if and only if modulus of trace of the determinant modular of trace of the Jacobian matrix at the point x star y star is less than 1 plus determinant of the Jacobian at the point x star y star less than 2, where Jacobian matrix J at x star y star is given by this matrix 2 by 2 matrix del f del x del f del y del g del x del g del y at the point x star y star. This is the first order nonlinear difference equation. This system is this, and the x star y star be a steady state. Obviously, x star equal to f of x star y star and y star equal to g of x star y star. If x star y star be a steady state of the system. Here xt plus 1 equal to xt equal to x star, and yt plus 1 equal to yt equal to y star. Linearization of the system about the point x star y star. Consider a small perturbation about x star y star, and this perturbation ut equal to xt minus x star and vt equal to yt minus y star. So xt equal to ut plus x star and yt equal to vt plus y star. Then the given system becomes ut plus 1 plus x star equal to f of ut plus x star comma vt plus y star, and vt plus 1 plus y star equal to g of ut plus x star comma vt plus y star. Now f of ut plus x star comma vt plus y star, and applying Taylor series expansion about the point x star y star and neglecting the second and higher order terms due to small perturbation utvt. So we get this nearly approximately equal to f of x star y star plus ut del x of f of x star y star vt del y of f of x star y star and plus dot 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 dot. This equal to x star plus ut del x of f of x star y star, because this f of x star y star equal to x star, because x star y star is an equilibrium point, so this plus vt del y of f of x star y star. Hence obviously this ut equal to ut del x of f of x star y star and vt del y of f of x star y star, because this equal to ut plus 1 plus x star. So cancel x star from both sides and we get ut plus 1 equal to this. Similarly, you can find v of t plus 1 equal to this vt, sorry, ut del x of g of x star y star plus vt del del y of g of x star y star. This is a linear approximation of the given system 1 about the point x star y star. Writing this in the matrix form of this system 4, capital U t plus 1 equal to j capital J U t plus 1 capital U t t. Here capital U t is the 2 by 1 matrix, column matrix U t v t. And obviously capital U t plus 1 is the column matrix, and this U t plus 1 v t plus 1. And capital J at the point x star y star equal to del f del x del f del y del g del x del g del y at the point x star y star. The eigenvalues of J determines the local stability of the system 1 at the point x star y star. The characteristic equation given by J minus lambda I, determinant of this equal to 0. So determinant of this A11 minus lambda I12, A21, A22 minus lambda, where A11, A12, A21, A22 is this matrix, 2 by 2 matrix. So this is the quadratic equation in lambda, lambda square minus trace of J into lambda plus determinant of J equal to 0. The equilibrium point x star y star is locally asymptotically stable if and only modulus of lambda j is less than 1, where j equal to 1 and 2. We'll prove that it is true if and only if modulus of trace j is less than 1 plus determinant of j less than 2. For this, we let f of lambda is the function of lambda equal to lambda square minus tau lambda plus delta, where tau is the trace of j at the point x star y star, delta is the determinant of j at the point x star y star. The characteristic equation is given by f lambda equal to 0, that is lambda square minus tau lambda plus delta equal to 0. So the roots of this equation are given by lambda 1, lambda 2, tau plus minus root over tau square minus 4 delta by 2. Here we got this formula. And there are two eigenvalues, lambda 1 and lambda 2, of this matrix G of x star y star. Now we have to show that modulus of lambda j is less than 1 at g equal to 1, 2, if and only if modulus of tau less than 1 plus delta less than 2. First, we have to prove that the condition is necessary. Suppose modulus of lambda j is less than 1, j equal to 1, 2. Then there are two cases. First case 1, eigenvalues are real. So obviously lambda square minus 4 lambda greater than equal to 0. That is tau square greater than equal to 4 lambda. So tau square minus 4 delta, tau square greater than equal to 4 delta. So tau square minus 4 delta is greater than equal to 0. Now f lambda equal to lambda square minus tau lambda plus delta. So we can write this tau lambda minus tau by 2 whole square plus delta minus tau square by 4. So f lambda minus 4 delta minus tau square whole divided by 4 equal to lambda minus tau by 2 whole square. So this is equal to lambda minus tau by 2 whole square equal to 4 into 1 by 4 is equal to f lambda minus 4 delta minus tau square by 4. Comparing with this equation, x minus h whole square equal to 4ay minus k is the parabola with hk vertex. So this is the parabola, forms a parabola. This is the lambda axis, that is the x-axis, lambda axis, and this is the y-axis, the f lambda. So this the vertex is the tau by 2, 4 delta minus tau square by 4. This is the vertex of this point. And parabola this f lambda equal to this cuts the lambda axis at 2 points, lambda 1, 0 is the point lambda 1, 0 and lambda 2, 0. Assume that lambda 2 is less than lambda 1. Then the lambda 1 is the tau by 2 plus half of root over of tau square minus 4 delta, and lambda 2 equal to tau by 2 minus root over of tau square minus 4 delta divided by 2. So lambda 1, 0 and lambda 2, 0 are equidistant from the point tau by 2, 0. From this point, lambda 1, 0 and lambda 2, 0, both of them equidistance, and the distance is this half of root over of tau square minus 4 delta, and this distance is also half of root over of tau square minus 4 delta. So though this distance from this point to this point and this point to this point, distance are same. Now modulus of lambda g is less than 1. So obviously minus 1 less than lambda 2 less than equal to tau by 2 less than equal to lambda 1 less than 1. So look at this figure. Then this implies minus 1 less than tau by 2 less than 1. So tau by 2 lies between the minus 1 and 1. So modulus of tau by 2 is less than 1. Squaring on both sides tau square by 4 less than 1. And now already we assume that tau square is greater than equal to 4 delta. So tau square by 4 is greater than equal to delta. So here this delta is less than equal to tau square by 4, and tau square by 4 is less than 1. So obviously delta is less than 1. This is the relation. Also tau by 2 less than equal to lambda 1 less than 1. This is the tau by 2 is the lambda 1, and this is the point 10. This is the point 1. So obviously lambda 1 lies between tau by 2 and 1. So tau by 2 less than equal to lambda less than equal to 1. Equal to means when these eigenvalues are equal, and minus 1 less than lambda 2 less than equal to tau by 2. So this is the tau by 2, this is the lambda 1, this is the 1, and this lambda 2, and this minus 1. Hence, this distance between the lambda 1 and tau by 2 is the modulus of tau by 2 minus lambda 1. Obviously, is less than modulus of tau by 2 minus 1. So obviously, this distance is tau by 2 minus 1. And obviously, tau by 2 minus lambda 2, this distance is less than equal to modulus of tau by 2 minus of 1. So this distance. Also, modulus of tau by 2 minus lambda I, sorry, this is the lambda j. Modulus of this equal to half of root over of tau square minus 4 delta, because this distance is the half of root over tau square minus 4 delta, tau square plus 4 delta. So this distance are equal. This is the tau by 2 minus lambda 1, and this is the modulus of tau by 2 minus lambda 1, and this distance is the tau by 2 minus lambda 2. This implies half of root over of tau square minus 4 delta is less than 1 minus modulus of tau by 2. So this squaring on both sides, we get this result, and after simplification we get modulus of tau less than 1 plus delta. Also delta is less than 1, so we get modulus of tau is less than 1 plus delta less than 2. So this is the result. And for case 2, if eigenvalues are complex, then tau square is less than 4 delta. Tau square is minus 4 delta is less than 0. Then the two complex eigenvalues, complex conjugate tau by 2 plus minus I means I square equal to root over I square equal to minus 1, half of root over of 4 delta minus tau square. Now modulus of lambda j square, this equals to modulus of lambda j square, this equals to first component real part square plus imaginary part square. So after simplification we get this delta, this is equal to delta. Now modulus of lambda j is less than 1. So modulus of lambda j square is less than 1. Hence modulus of lambda j square equals to delta is less than 1. Also tau square less than 4 delta. Tau square less than 4 delta. Our assumption is this. So this implies modulus of tau less than root over 2 into root over of delta. So modulus of tau is less than 2 root over delta, that is less than 1 plus delta, because 1 minus delta root delta square, this greater than equal to 0. So 1 plus delta minus 2 root delta is greater than 0. So 1 plus delta is greater than 2 root delta. So we get this modulus of tau is less than 1 plus delta less than 2. Next, to prove the condition is sufficient, suppose that this delta is less than 1 and the modulus of tau is less than 1 plus delta less than 2. Then also there are two cases. First case, eigenvalues are real, tau square greater than equal to 4 delta, and lambda 1 is this, lambda 2 is this, and lambda 2 less than lambda 1. Now modulus of tau less than 1 plus delta, so this implies minus delta is less than 1 plus modulus of tau. So this implies adding tau square by 4 on both sides, we get this, and after simplification we get this result. So modulus of tau by 2 plus root over of tau square minus 4 delta by 2 less than 1. Now this modulus of tau means plus tau and minus tau. So for plus tau by 2, so we get this the lambda 1. So lambda 1 is less than 1. And when mod tau, that is when minus tau by 2, this less than 1. So tau by 2 minus root over of this is greater than minus 1. So this is the lambda 2. So obviously we find modulus of lambda j is less than 1 for j equal to 1 and 2. And case 2, when eigenvalues are complex, that is tau square less than 4 delta. So complex conjugate eigenvalues are lambda 1, lambda 2, tau by 2 plus minus I root over 4 delta minus tau square by 2 whole divided by 2, and lambda j, mod of lambda j square, this equals to real part square plus imaginary part square, this equal to delta after simplification. Now tau square less than 4 delta, so tau square by 4 less than delta less than 1. This delta less than was given. This implies modulus of lambda j square is less than 1. Modulus of, because delta is the modulus of lambda j square. So modulus of lambda j square is less than 1. So obviously modulus of lambda j less than 1. This is completes the proof. Note that the equilibrium point x star y star is unstable if some lambda j modulus of lambda j greater than 1. If either lambda 1 modulus of lambda 1 greater than 1 or modulus lambda 2 greater than 1. That is, if any one of the following is satisfied, if trace of j is greater than 1 plus determinant j at the point x star y star, or trace of j less than minus 1 minus delta j star at the point x star y star, or condition 3, determinant of j greater than 1 at the point x star y star, for then we see that this equilibrium point is unstable. Thank you for watching this video.